I'm actually at the University of Illinois, Chicago now, but it's not a mistake because when this conference was first being organized, I was there. So in any case, it's a pleasure to get a talk. Thank you so much for the invitation. I've been looking forward to this for 2.5 years, so I'm glad it could finally happen. So I want to use, let me say right off the bat, this is all a joint work with Jacob Zimmerman. So I want to use this talk to sort of set up some ideas connected to Hodge theory and transcendence of both numbers and of functions. Since this is sort of before even some of the introductory tutorial talks, I'm going to try to not get too much into the weeds, so make it more of an overview. But hopefully, if things don't make sense in this talk, hopefully they will make sense by the end of the week. So let's start with K being a subfield of the complex numbers. And let's take X over K, a smooth projective variety. Okay, so the theme of this talk is going to be that somehow the Hodge theory of the cohomology of X and the transcendence thereof should sort of detect the geometry. And of course, we all know one way that geometry is detected by Hodge theory, via the Hodge conjecture. Not talking about that. This is in some sense a more elementary way that the sort of Hodge structures on the cohomology of X are going to detect algebraic geometry. Okay, so what are we going to do? Well, we're going to take, on the one hand, what we'll call the Betti cohomology of X, by which I just mean that we take the degree I cohomology of the C points of X, considered as, with its Euclidean topology, with Q coefficients. Okay, so this is a Q vector space. And this is a vector space that sort of Q forms on topological I cycles. Okay, so this is a very topological gadget. And on the other hand, we can form sort of a corresponding algebraic object called Durham cohomology, degree I Durham cohomology, which is now a K vector space. And we should think of this as being, a typical class, and here is the class of a closed K-rational algebraic differential form. The RAM classes of K-rational differential forms. Or in other words, differential forms that are defined on this space. Okay. And these two vector spaces are canonically equipped with an isomorphism over the complex numbers, which is given by integration. Okay, so once I tensor up, on the one hand, this guy over K by C, and on the other hand, this guy over Q with C, I get an isomorphism, which is again just integration. So explicitly, I take the class of some K-rational differential form, and I associate to it the Q form, which takes an I cycle gamma and sends it to the integral of omega over gamma, which is a complex number. So it's a C-valued form on this the homology. Okay, so the basic principle underlying what I'm going to be talking about is that this isomorphism should be highly transcendental unless it has a reason not to be transcendental, namely one coming from geometry. Okay? So here's the principle. So these periods, these integrals of K-rational forms over topological cycles algebraic relations between them, between the periods, should come from geometry. Okay, so how do we make this conjecture precise, or this principle precise? Well, this is done in what's called Grothendieck's period conjecture, which says the following. Let's start with an algebraic variety X defined over the rations. Okay, so on the one hand, how do I, understand algebraic relations between the periods? Well, that's not so difficult to quantify. We can look at the transcendence degree of the field they generate over Q. So I just take Q, adjoin all of these intervals. All these, we'll just call them periods. Periods of degree I cohomology. Okay. This is some measure of how many algebraic relations there are between these periods. Now, how should I understand the ones that are sort of, how, to what extent we should have transcendence, coming from geometry? Well, for that, we use what's called the motivic-Galois group, which I'll say a few words about. It doesn't really matter for this talk, the precise definition here. So what is this gadget? Well, you take your favorite Tannakian category of motives over Q. Okay, so that's a lot of words. Motives over Q, you should think of this as sort of some kind of universal cohomology theory. Okay, so a typical element in here looks like sort of degree I cohomology of X, maybe. And this specializes to all sort of reasonable cohomology theories of X. So for instance, it specializes to the theorem cohomology, and it specializes to Betty cohomology, and it specializes to other cohomologies. Okay, and why am I taking a Tannakian category of motives? Well, being Tannakian means that this abelian category of sort of universal cohomologies is equivalent to representations of some pro-algebraic group. This is equal to representations of some group, which I'll just call the motivic-Galois group of Q. Okay, and so how does this work? Well, the object HIX, for instance, corresponds to some representation of this group valued in GL of the Betty cohomology. Okay, so this corresponds to a representation rho of this motivic-Galois group, which is some big complicated thing, into just GL of the Betty cohomology. Thanks. Just some finite dimensional Q vector space. Okay. And the image of this representation is what this is, some subgroup of this much more reasonable finite type general linear group. Okay. Now, why is this capturing sort of, how much algebraic geometry is accounting for relations between the periods? Well, if the image of this representation is smaller, then it's sort of easier to have on the level of representations maps between, this and its tensor powers, which corresponds to having sort of more correspondences between X and its tensor powers, all of which sort of come from geometry in this motivic category by construction. Okay, so the smaller the representation, the sort of more maps between them you have, and therefore there's sort of more redundancy among the periods. And this conjecture says that these two should be equal. Okay, let me at least say in words that there's a version of this. There's a slight generalization to this conjecture due to Kontsevich and Zalgier, which somehow says that if you look at all periods of all algebraic varieties defined over Q, sort of the only relations on that are the ones coming from pullback and push forward. So those are sort of the geometric relations, and like Stokes' theorem. Okay, so it's a bit of a stronger statement. I'm not going to write it down, but I will come back to that later on.
Finite positive entities can So temperature that here also be translated into the finite quality of integers.
So the consecutive Zagay statement, so you make sort of a ring of formal periods, which only have the relations that I said, coming from pull back, push forward, and Stokes theorem, and it has like an evaluation map to C. Okay, so their conjecture is basically that this is injective. And that comes down, I mean, when you sort of work through everything that you can prove just with the formalism, that works out to sort of this transcendent statement, which basically says that that's C point, and a statement about the ring being an integral domain, right? Connected to statement. Okay, so yeah, that's the additional information needed. Some connectedness statement. Okay, so this conjecture is wonderful. It somehow is slightly unsatisfying from a couple perspectives. Sort of from an algebraic geometrist perspective, it's sort of, only works for algebraic varieties defined over Q, whereas you might be interested in algebraic varieties defined over other fields. From the perspective of transcendental number theory, if you sort of write down sort of transcendence statements you get here, there's sort of a lot of transcendence statements that don't follow from this conjecture. For instance, the Shanuel conjecture that we learned about in the last talk. Okay, so there's an alternative version of this, sort of a vast generalization. But when I write it down, it's going to look very simple. And this is due to Andre. Oh, I should say before I, since we phrased everything motivically anyway, this conjecture we may as well upgrade to just any motive over Q. Right? Just replace HI everywhere with the motive that we're talking about. Okay. And in all these definitions, it's the same definitions. Motive corresponds to a representation on the Betty realization of this motive. And it's the same definition of this group. Okay, so what does Andre say? Andre says, well, let's not restrict ourselves to motives over Q. Let's take an arbitrary subfield of C. Take any motive over this bigger field L, over L motive. Well, then we should have the same relationship, or at least the non-trivial side of this relationship. So in other words, the transcendence degree over Q of L adjoin the periods of M should always be bigger than or equal to the dimension of this motivic L1. Okay, why bigger than or equal to? Well, because we have no control over L anymore. So you could make L bigger and bigger, and somehow, if L is bigger than the field of definition you need for M, then this side isn't going to change, but this side is going to get bigger. So you only expect an inequality in general. And indeed, in this special case, you can prove the inequality in the other direction pretty easily. So sort of this is the important part of the inequality. Now, why is this generalization interesting? Well, it's interesting for a variety of reasons, but one reason it's interesting is that, yeah. Are you asking, should you get equality if you take the minimum? I don't know if you should. Because that's correct. Yes, my explanation is an easy reason you should only expect inequality. Not all the reasons you should expect inequality. But why is this? Why do I find this conjecture interesting? Well, it's interesting because it kind of mixes, transcendence of numbers with algebraic parameters, like families of algebraic varieties. And why do I say that? Well, if you're interested in testing the algebraic independence of a certain period that shows up with some other transcendental number, which you can include in the ground field, L of your motive, okay? On the left-hand side, you get some statement that's actually quantifying the transcendence of those numbers. Whereas on the right-hand side, this is a totally algebraic thing. So if you stuff some transcendentals into L, they just appear on the right-hand side as an algebraic parameter. Okay, so this is some object that starts seeing the behavior of this motive in families as opposed to sort of a transcendent statement about actual numbers.
I'm going to ask you a dumb question. What if you took L equals C?
And the left-hand side.
Well, the left-hand side is quite big
Because
because it's transcendence over Q.
Oh, I see. Okay, that's.
And this-
Yeah.
Let's go for it. Yeah, no, great. Please ask. Okay, so that's kind of a vague reason why this conjecture is cool. The other reason it's cool is that it exactly recovers the Shanuel conjecture we were learning about before. Okay, so let's go through that in detail. That's a very useful example to think about. Okay, so let's take alpha 1 through alpha n inside of C star. This is just some list of numbers which are multiplicatively independent. By which I mean the sort of subgroup they generate is rank n. Okay. Now, what is the motive I want to consider? Well, let's take the motive which universally computes the relative H1 of GM, so C star, comma this subset, where I also include 1. Okay. So what is the field of definition of this motive? Well, obviously, it's defined over the field L, which is Q adjoint alpha 1 through alpha n. Okay. Now, what are the periods that show up here? Well, GM is affine, so the only sort of actual algebraic forms that I need to consider, or the Durand classes I need to consider, are actual algebraic forms. And the only one that gives anything interesting is the logarithmic form, dq over q. Okay, so the periods that show up here are integrals of dq over q over, 1 cycles, except since I'm taking relative cohomology, I have to allow relatively closed cycles. So what shows up? Well, there's the loop that goes around the origin, and then there's the loops that go, say, from 1 to any of the alpha i's. So there's sort of 2 types of paths that show up. And if I integrate this over this loop, I get 2 pi I. And if I integrate over here, I get log alpha I. Okay, so on the left-hand side, we're getting, how far down can people see with this here? Can I go down? Yep. Okay. So on the left-hand side, we're getting that the transcendence degree over Q of Q adjoin, well, I need to have L in there, so that's alpha 1 through alpha n. And then I need to adjoin all the periods, so that's 2 pi I and all of these logs. Is bigger than or equal to, and then we have the sort of hard part of this inequality. How do we understand this? Well, it turns out for 1 motives, we can pretty precisely understand this in terms of Hodge theory. And again, if what I'm about to say doesn't make so much sense, then you can ignore it. But what ends up showing up here is the Maupertuis curve of this for a 1 motive. This is Andre shows this. And in this case, it's an extension of GM by n copies of GA. So we get n plus 1. Okay. So in particular, if I forget about the 2 pi I, and I relabel, I call my log alpha I beta I, and alpha i's are then e to the beta I exactly end up with the Shanuel that we talked about last. This is bigger than or equal to n. Okay, this is useful because it sort of, in a very concrete way, tells us how much more powerful the Andre version of the conjecture is versus the Grothendieck conjecture, right? Because the Grothendieck conjecture only applies if this motive is defined over Q or maybe over a number field. So it needs the alpha i's to be algebraic numbers. Okay. So the statement I get here from the Grothendieck period conjecture is the Lindemann-Weierstrass theorem, that the exponentials of algebraic numbers are maximally transparently independent. Well, I mean, I had a 2 pi I in here, and it was bigger than or equal to n plus 1. So if I drop the 2 pi I, this had better be bigger than or equal to n. No. Okay, so the sort of Andre version is more powerful than the Grothendieck version in exactly the same way that the Shanuel conjecture is stronger than the Lindemann-Weierstrass theorem Okay, so in particular, the Shiny conjecture is very much, still open with the Midrasha theorem and theorem for quite some time now. And it's even in sort of very small n, this is, maybe this was mentioned last lecture, but this in particular implies that like E and pi are transitively independent. So like that, even that we don't know. That's like a pretty easy square case. Okay, great. So that's the sort of interaction between sort of periods of algebraic varieties and the transcendence of actual numbers. Okay. So now we're going to transition to functional versions of all these statements. And functional versions are nice because we can actually prove some things. So I apologize to the note takers, but I will post some slides of this talk, so you don't have to religiously write down everything. But I'm basically just going to take all the statements on the board and replace them with their functional analog. Okay. So up here, rather than taking Q as my base field, I want to now take the complex function field of a complex algebraic variety. So let S be a complex algebraic variety. And we'll take K to be its complex function. Okay. And we'll probably need a base point there, sporadically. So let me give myself a base point. Okay, we're still going to be talking about a smooth projective X over K. Really, sort of internally, you should think of this as like an actual family of algebraic varieties over S, possibly up to shrinking S. Okay. Okay, now we still have Betty cohomology, except now it's not a Q vector space, it's a Q local system, right? Because the appropriate thing to take here is just Ri F push forward QXN. Okay, so now this is a Q local system. And you should still think of this as Q forms on fiber-wise topological I cycles. Okay, now what about the Durham side? What kind of structure do I get here? Well, I can still talk about Durham classes of now fiber-wise closed K-rational differential forms. Fiber-wise closed. So what is this? Maybe I'll call this over S. Maybe I'll put that in the definition over here to over S. This is an algebraic flat vector bundle. Okay, so this is some vector bundle downstairs, and it comes equipped with the Gauss-Manin connection, which is the sort of algebraic flat connection on here. And we still have a comparison. How does the comparison work? Well, essentially, I perform this integration, but now on fibers, and it's going to be valued in analytic function, because what I get when I sort of integrate a fiber-wise closed algebraic form along some flat family of cycles is analytic functions. Okay, so let's make this more precise. So, yes, I can tensor over sort of the algebraic stock of regular functions at my base point with what I'll call Kn, which is just germs of meromorphic functions at S naught.
Wait, your base point is a geometric point over the generic point of that, or is it like a particular point?
So you're right that there's some discordance here because I said we may need to start shrinking S, and maybe I lose my base point. So we do this in the paper. There's a couple ways to remedy that. The best way to remedy that is you don't take S not to actually be a point, but like a little arc or a germ of an arc, and then you can always make sense of restricting to that point. But whatever, let's just ignore that.
You can just take it to be a geometric, the algebraic closure of the event. back to the algebraic equation.
Well, no, you can't exactly do that. So, yeah, no, not exactly, because we want on some level this to be valued in the complex numbers sort of fiber-wise. And if you take like a random point here, have some kind of embedded. But anyway, let's not get into that. We can talk about it later. Just pretend that you have a point that for any model you have your base point S naught happens to be in the base of that one. That doesn't 100% make sense. And what am I doing here? Well, I'm taking the stock at the base point and tensoring over Q with Kn. And I claim I have an isomorphism given by fiber-wise integration between this and this. And what does that do? Well, it sends the class of a fiber-wise closed algebraic differential form omega to the form valued now in terms of meromorphic functions at S naught. What was that here? Which just sends a homology class gamma to the function, which is integrate omega on the fiber over S over the cycle I get by flatly transporting gamma to nearby fiber. Okay, so this is all happening locally around S naught. So you can take your homology cycle gamma and sort of move it to nearby fibers. You can integrate omega, restricted to that fiber along that cycle, and you get some function which is analytic in S. And that association of gamma to this analytic function gives me a form on I cycles value in the analytic. Okay. Wonderful. Okay. So, like I said, in the functional setting, conjectures become theorems. So, the Grothendieck version of this theory conjecture is the theorem that's due to Nori in the U. Okay, once again, it says that let M be a motive over K. Okay. And it's almost the same thing here, where I sort of replace every Q with my new ground field K. Except on the right-hand side, I have to be a little bit careful because this motivic group of M captures the sort of absolute geometry of M. And in particular, we want to sort of treat, all the stuff coming from trivial families of algebraic varieties should be treated sort of equally. I should be getting no transcendence just from having transcendental periods that show up over a fiber in that sort of trivial family of algebraic varieties. So I somehow need to modify this so that I'm only seeing transcendence coming from actual variation in the family. Okay, and there's a fairly easy way to do this. I mean, I'll say it in words because I'm probably not going to give too much meaning. But what should this thing be? Well, instead of looking, before I took the image of the motivic Galois group of my base field, right, in GL of the Betty cohomology, okay, and that was this group. It's just the image of the representation that this motive corresponds to via the Tanaka duality. Well, now I just kill all the stuff that comes from trivial family. So, I have a base change map from motives over C to motives over K by just taking the corresponding trivial family. And that gives me a map of Tanakian groups in the reverse direction. So I have a map like this. And I just take the kernel of that. Okay. Oops, sorry. Kernel of this. And the image of that is what this is going to be. Okay, that's still a little complicated. Something that's really nice in the functional setting is actually we can extremely concretely say what this group is. It's exactly the Zariski closure of the monodromy representation of this local system. Okay, in fact, I'll put it down here. In fact, G motivic of M is just the algebraic monodromy of the Betty realization of M, which is just a local system. And by algebraic monodromy, I just mean the Zariski closure of the image of pi1 in the corresponding monodromy representation. Not the connecting commodity, yes. Maybe pi1. Yes, since we're only going to be viewing this through the dimension, I'm going to ignore that. But yes, there is one does need to be careful with connecting. Any other questions about this? I'm being a little precise here, but hopefully it's clear what I mean. Again, let me just say it in words. This, if I look at the Betti realization, I mean, think of M as coming from an actual family of algebraic varieties. I get this local system. It comes with a representation of pi1 into GL of this Q vector space. I'm taking the image of that and taking the Zariski closure. That's an algebraic group. That's what this ends up being. Great. Now, what is the Andre version of this conjecture? This is also theorem. This is sort of theorem 1 I'm going to be talking about today. And it says, well, where before we had Q, we now have K. So I should take K here. Where are the periods valued? They're valued in what in this field I'm calling Kn. So I should take any intermediate field between K and Kn and take a motive over it. Okay. And then the transcendence statement should be the transcendence over K of L adjoin the periods of M is bigger than or equal to. Sorry, I didn't give a name to this. This is called the relative motive group. Yes, it's just the field of germs of meromorphic functions near the base. Yeah. Okay, but that's a good question because there's something a little fishy happening here, which I didn't call attention to over here, which is that in the sort of transcendence of numbers statements, it was important that our periods of M were valued in whatever this field was, C, right? In the field of comparison between the Betti and the Durand homologies. Okay, so what does it mean? I mean, if I have a motive M over L, I need to have periods that are valued in Kn. Okay, what does that actually mean? These should be Kn periods, right? Because the normal, if I just think of the periods of M in this sense, they would be valued in the germs of meromorphic functions sort of on L. Okay, so what is going on here? So what are Kn periods? Okay, well, let's just think about the actual geometry corresponding to this tower of fields. Okay, so K, as we've said, is the complex function field of S. Okay, for this transcendence statement, we may as well assume L is finitely generated. So L is also the function field of an algebraic variety. Let's call that T. Okay, the embedding of K into L means that T has a map to S, possibly after shrinking stuff. Okay, so we have an algebraic map from T to S. Now, what about the field embedding of L into the meromorphic function germs at some base point of S? Well, what that means is if I analytify this map, oh yes, that is unfortunate.
But also, it's good because I can ask one question.
Yeah, go ahead. Yeah.
So, I may as well assume that L is a function field that you cannot. I mean, it's really an assumption.
Well, I mean, we may as well assume that L is finally generated with K.
Yeah, but that's not part of the assumption.
No, but this is clearly true if L is not finite transcendence degree. But this is infinite and this is not.
Oh, okay.
Yeah. No, yeah, it's
Thank you.
yeah, sure. Okay, so that's G. This is G. And what does it mean to have an embedding of K and Kn? Well, that means I have some section of this map, some analytic section of this map over some neighborhood of my base point. Right? Because under this map, this embedding just becomes pullback of the coordinate function density. Okay. So then what are the Kn periods? Well, I take M, which you should think of as sort of a family of algebraic varieties over T. I take its usual periods as functions over T, and then I pull them back via this analytic section, and now I have analytic functions on S, which are then valued in Kn. And so what this Andre version of the period conjecture is saying is some stronger transcendence statement about take the periods of motives over T and pull them back in this way along analytic section. And indeed, I mean, the transcendence degree might drop if you restrict to this thing. So it is, it's a stronger statement. Okay, so do I have anything else? Maybe let's talk a little bit about the Shanuel conjecture, which in the functional setting is a theorem due to X. So let me be as sparse as I can be. Well, I'll be a little sketchy here, but basically in this setup, so I switched to betas at the end because that's typically the way the Shanuel conjecture is written. So let me start with betas then. So now in the functional version that you may be used to, we start with beta 1 through beta n, which are now just formal power series in some variables, let's say T1 to Tl. And we have to assume the analog of them being multiplicatively, their exponentials being multiplicatively independent. That's the same as saying that these should be Q linearly independent marginal constants. Okay, so all I want to say, I just want to relate sort of this picture to this Shanuel setting. So, I mean, these n functions, formal power series in these coordinates 1 through the T1 to TL, you should think of as an actual analytic map from a ball B in sort of C to the L into GM to the N. Okay, we have GM the N, and we have a ball B, which is inside of C to the L. Okay, and these betas or the exponentials thereof give us a map like this. Okay, now that image may not be Zariski closed. Let's give a name to the Zariski closure. Let's call it T. Sort of the image data. Okay, so how do I sort of pass from this picture to this picture? Well, it's by a sort of very simple observation, but kind of a powerful one. If I can find some algebraic projection onto some affine space, say, call it AM. I already can call it R, which is quasi finite on this T. Okay, and then by the inverse function theorem, I may as well assume that this B is actually a ball inside here. Okay, so by sort of eliminating, by taking, the point is I can find algebraic coordinates on B such that this picture that I had before actually looks like this picture I have over here. Okay, and then indeed the Shanuel theorem is exactly the output of this theorem in this context. And why is that? Well, if we're taking B to be a ball in this affine space of dimension R, this R is exactly the rank of the Jacobian matrix of the betas. Okay, so the statement that I end up with is that the transcendence degree of L adjoin the periods over K. So that's the transcendence, that's how to say, that's the transcendence degree of C adjoin of this. Let me just write it. Okay, if I took it over C, well, I mean, this conjecture, I mean, this theorem is measuring transcendence degree over K, so I need to subtract out the dimension of what is S over here, which is just the rank of the Jacobians, and minus the rank of the Jacobian, should be bigger than or equal to N. Okay, so that is the statement of the sort of functional version of Shanuel, which is the theorem of X. This is. Yeah, so this is actually next to them, which may be something which you see. Okay, cool. Any questions so far? Yeah. So, variance of the There absolutely is. So I should have mentioned this, and I was going to come back to it, but in fact, they prove what is the antibody. I can tell you more about what it is. It's if you think about it in the way I was describing it before about sort of some formal period ring being an integral domain, that's exactly the piece that's missing from this, and they also. Okay, so let's go through this one more time. This was the sort of functional version of these transcendence statements applied to sort of the comparison between Betty realization, namely this local system of the cohomologies of the fibers, and the sort of theorem realization, which was the space of sort of algebraic forms. And let's go one step further. So now, instead of actually having an algebraic family of varieties, let's just keep track of a complex local system. Okay, so let's still have S a complex algebraic variety. So let's take V to be a complex local system. Okay, and I claim this basic comparison we still have, even without the geometry underlying it. Okay, well, obviously the Betty realization of this complex local system is tautological. It's just V. This is a C local system. But it turns out to any complex local system on an algebraic variety, there's a canonical algebraic structure. And that's what we call the theorem side of this. We'll call it curly V. This is the canonical algebraic structure. Okay, and it is an algebraic flat vector bundle such that if I tensor up with analytic functions, let's do a little more careful here. Now we're going to do this globally. Okay, so there's two ways to build an analytic flat vector bundle from either of these. We can take my complex local system and then just tensor over C with analytic functions. Or I can take this algebraic flat vector bundle, early V, and tensor over OS with OSN. And these are naturally equivalent. Okay, that's what it means to have an algebraic structure on this. Okay. So you should think of this comparison as being sort of a comparison between the Betty realization of this complex local system and what you might call the theorem realization, which is some canonical algebraic structure. This map is nothing more than the sort of change. I mean, how to say the matrix of this map of this comparison is exactly the sort of change of basis between an algebraic frame and a flat. Okay, so how do we sort of geometrically understand all of these transcendence statements? Well, we can understand them geometrically by looking at the sort of algebraic variety parametrizing such comparisons. Okay, so let I be the algebraic variety of sort of fiber-wise comparisons. So these are, let me call it phi. Sorry? Well, yeah, the canonical algebraic structure is the unique one with regular singular.
But there, Francis, don't you have to decide something about like if there's some simple mononomial?
Yes, that's true. And yes, strictly speaking, I should. Yes, but it's not going to matter. Yeah, it's not going to matter. Sorry?
There's more than one canonical.
Yes, that's correct.
It's not canonical, it's just regular singular.
Well, actually, the algebraic structure here is canonical. It's the extension. Okay, so let's let I be the algebraic variety of sort of comparisons, by which I mean choose some point S of big S and choose an isomorphism between the fiber of curly V with the fiber of V over my base. Okay, so this is some algebraic variety. The algebraic coordinates on this Sorry? So,
What is the lower AC?
so I am being a little imprecise here, but this is sort of as a, if I want to think of the actual complex points of this algebraic variety, it's take a point little s and big S, complex point, and take the fiber over that and choose some isomorphism. Okay. So if you want, this is sort of the
But the AC is not fixed.
little s is not fixed. Okay, so in particular, this has a projection map to big S, which just sends, I just looked at little s. Okay. So this is an algebraic variety, and its algebraic coordinates are just given by taking the matrix of this comparison with respect to the sort of algebraic coordinates on the source and whatever my fixed coordinates on the term. Okay, the target vector space is fixed. Okay. Is it clear what I mean by this? I was hoping this would be more clear to people less familiar with algebraic geometry. But anyway, okay. Well, let me also, this is like the total space of like the Hom. There's a natural flat vector bundle that's just Homs from V.
Yes, yes, for me.
Okay, so let me also write this.
I think then you should at least write S to multiply it. At least that. At least that.
That's, oh, yeah. Well, phi can, oh, yeah. Okay. Yes,
least that.
sure.
Yeah.
Okay.
But they're
Yes.
are they both vector spaces over the same view? Is there, like a little-
Well, this is, yeah, over C, because this is a complex local system. I'm sorry, I've taken a step beyond sort of geometric setup before. This is just about a complex local system.
Yeah.
And the associated canonical algebra.
The fiber of but it's just, it's a GLN toward the.
Yeah. That's exactly where I'm going with this. Okay, so what is this object? So this is the sub of the total space of just all Homs, which are isomorphisms. Okay, that's an algebraic variety. It naturally has an action by acting on the target of GL VSO. Okay, and obviously that's going to act transitively on fibers over S. Okay, so this is a principal GL VS naught bundle. What other structure does this have? Well, it naturally has a flat connection inherited from the flat connection here, right? So if I take a particular S comma phi, okay, I can take the matrix with respect to a flat frame here, and I just use the same matrix and transport it to nearby fibers in that way, and that gives me a flat structure to this principal GLVS naught bundle. Okay, wonderful. And in fact, we even know one of the leaves that show up in this flat bundle. So it has algebraic flat connection. Here's an example. The leaf obtained by analytically continuing the identity map is exactly the locus of parallel transport operation. There is the point S naught comma identity.
But then you have to identify the algebraic fiber with the flat fiber.
Yes, that's true. Okay. Well, okay, yes. So choose.
You have to make a choice that you can focus.
Yes, choose. I'll say M identity.
So
No, you're right. Okay, which I think of as a point, S naught comma identity. Point in here. And as I, parallel F, as I transport that via the connection, I'm just going to recover the parallel transport operators from the fiber over S to the fiber over S naught, over that choice of homotopy class of point between S and S. Homotopy class of path and S. Okay, sorry, I didn't need to get too far into this. So let me just call sigma B equals corresponding leaf, which is sort of parallel transport. Okay. Now, take too much. So I have this I, it has this projection map. I have this sigma v sitting inside it, therefore also maps to S. Okay, this is a torsor for GL of VS naught. Okay, this is preserved by the action of the image of the monodromy representation, right? Because this is exactly the locus of parallel transport operators. So if I act by monodromy, I just come back to a different parallel transport operator. Okay, so this is preserved by the image of pi1. So if I take the Zariski closure, which I'll call PV, this is preserved by the Zariski closure of the image of pi1, which is what I was calling the algebraic monodromy. Okay. So the fact that, so here's a fact, PV is a principal GB bundle. Or more explicitly, this PV is exactly take your sigma V and translate it around by the C points of the algebraic model. Okay, so
GB is the
GB is the algebraic model. Yeah. So let me just make two quick comments about this. This Zariski closure certainly contains this, right? Because the fibers of this have a transitive action by the image of the monodromy representation. But the Zariski closure had better also, act on the fibers. But of course, it could be bigger. Okay, and the statement that we have equality here can therefore be tested on by a dimension count. And what we need is that the dimension of this is exactly the dimension of GB plus the dimension of S. Okay, which is exactly the theorem of Nori and U, as I stated. Right? We need to say that dimension of PV minus the dimension of S is equal to dim GB. Okay, this is exactly the transcendence degree of the change of basis matrix between the algebraic and the flat frames over the base field, the function field of S.
Sorry, GB is the Zariski clause of the monodromy, right?
Yes.
So it doesn't include the function field.
Very much. Yes.
So these vectors.
V is the complex multiplicity.
Yeah, but when I write sigma V,
Yes.
I thought this small. I thought it stands for it's to the vector in one fiber.
No. This is a capital V. Yeah.
like parallel transport around all.
Yeah. So you take this like choice of identity at some point,
okay,
and you move it all the way around to everywhere, and you get some sort of multi-section.
But I have another.
Yeah.
PV, the GLD, do they meet or they're like this?
The PV and the
One
G.
guy acting on the left and the other on the.
No, oh, sorry. This is not meaning they act on different sides. All the actions are left actions.
All that. So they don't
I just wrote this one on the right because I didn't have the other one.
But they can move. Oh,
No, it's a sub action. The stabilizer of PV under this is
GLD. So PV is subset of GLD.
Yeah, because it's
Yes.
doesn't have one of them.
yes.
Pulling out. Now I'm trying to.
Okay, sorry. So let me now state a theorem, which is the sort of geometric version of this functional Andre conjecture. And it's going to be a statement about atypical intersections. Here's sort of theorem 2. Okay, so suppose V underlies a variation of mixed Hodge structures, whatever, quasi-polarizable, the integral, admissible. So it's something that looks like it's coming from a family, but we don't need the family. And take W inside of PV, an algebraic variety. And suppose it has an atypical intersection with this locus of parallel transport. Suppose U V. What does it mean for it to be too big? What does it mean for it to be atypical? Well, you would expect, the codimension of sigma V in PV, because it's a multi-section, is just the dimension of the grid GV. So we ask that the codimension of U inside W be strictly less in the dimension. Then, what is the conclusion? Well, if I take V and restrict it to the, if I project this component U down to S and take Zariski closure, right? So that's some algebraic subvariety of S, which I can restrict V to, then this has strictly smaller algebraic monodromy. Okay, so why did I take the somehow maybe overly complicated route to the second version of the theorem? Well, the point is that first version, that theorem 1, which was just straightforward transcendent statement about the functions that show up as the periods of families of algebraic varieties, is equivalent to this theorem, for variations. Okay, so that 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 functional Andre Grothendieck conjecture is equivalent to an atypical intersection state. Okay? And I'm going to go through the equivalent. It's not hard, but I certainly don't have time for that. Let me just make that as a remark. Yeah, so if you take this statement and restrict it to variations coming from geometry, then this theorem is equivalent to the theorem. Okay, so theorem 1, same as theorem 2 for symmetry. Sorry? I don't have it anymore, but it was in the same place. No, sorry, it was on this board. But that was like the Andre, that was the functional Andre conjecture. So the statement that the transcendent degree of like the periods of my motive over L, the transcendence degree over K was bigger than or equal to the dimension of GB. No. Sorry, I think things get a little garbled. The second remark I want to make, to go between the two. Yeah, sure. So it's actually, so to go from, let's see, to show that I mean, if you remember the example I did with deriving the sort of functional X-annual theorem, because we know that the X-annual theorem is an atypical intersection statement. So that kind of deduction is exactly the same as the implication of the first version of the theorem implying the second thing. Okay. So in other words, this sort of you take, I mean, in the context of in the Andre Grothendieck setup, you have this like analytic section. The U you take is just the image of that analytic section. Okay? And the W you take is the Zariski closure of it. And to go in reverse, you use this projection trick. You have a U, you take some projection that sort of captures all of the dimension, and then that gets you into the Andre Grothendieck section. Sorry, I'm running out of time. So let me get to some mistakes. I didn't want to finish with in a very short example, but I did want to write a few remarks first. So second remark, maybe I'll just make verbally. Hodge theory, and we'll probably see this later this week, tells you that having smaller algebraic monodromy for a variation of Hodge structure is the same as having more Hodge classes. Okay, so this drop in the algebraic monodromy is sort of tied to the appearance of more geometry, assuming the Hodge conjecture. But actually, we can make precise of this drop in dimension coming from geometry using this motivic Galois group in the theorem, right? There's no, you don't need to assume the Hodge conjecture for these statements. And then the last remark I want to make is this theorem, or if you want theorem 1, sort of implies all other Hodge theoretic X-annuals type statements. And this I do want to go through because it sort of makes it a lot more concrete what's actually going on here. So let me just take, let me take 3 more. When did I start late, right? Oh, okay. Well, Okay, let me just sorry about this. Let me very quickly.
That's why place, and they're gonna say something,
Yes, so this should be an admissible, probably polarizable integration, integral variation and such. Yes. No. Okay, so let me just end very quickly with an example. So I just want to kind of survey what all the different Hodge theoretic action annuals give you in a sort of common setup. Let me take n elliptic curves over S. Okay, and let's suppose that we have sections of each of them. Let me call the section, I don't know, sigma I. And let's suppose we have some algebraic form omega I on each one we have an algorithm. Okay, so the sort of version of Action-Annual for pure variations of Hodge structures, which was proven in the case of more varieties by Mach and Silverman, and proven by us for pure variations of Hodge structures. Well, what are the coordinates of the period map showing up here? They're these sort of tau I functions, which are just the ratio of the periods. Okay, so the alpha i's and beta i's are what you would expect. You sort of take a basis for the homology. You take this ratio, and the sort of pure version of Action-Annual says you have n functions here. Okay, if the transcendence of these functions drops by m on a locus of codimension smaller than m, then it has to be for some geometric reason. The geometric reason being some of these guys have to become either isotrivial or isogynous over that analytic locus. Okay. Now, what does the sort of mixed version tell you? This was proven for the universal family of abelian varieties by Gao and Teen, and then by Chu and Klinger, Gao, independently in one. Yeah, I don't know why you forgetting the order of the alphabet. Sorry. So what are the mixed period coordinates? Well, now I have, because of the section, I have some relative cycle floating around. Let me call that gamma I, which sort of goes from 0 to sigma I. Okay, and the mixed version of Action-Annual tells you, well, if I take the two n functions, which are tau I, and now the ratio of the relative period with one of the absolute ones. Okay, so I have two n functions. If their transcendence drops by m on an analytic locus of codimension smaller than m, then it's for a reason. The reason in this context being either some of them are isogynous or isotrivial, or some of the sections are torsion. Okay, and finally, the sort of version that I'm talking about is the same kind of statement, except now you just directly work periods. So this is kind of the point. Point is that if the transcendence of period maps ultimately are about the sort of Grassmannian coordinates of the Hodge filtration. So there's some kind of ratio of periods. And so you're kind of indirectly asking statements about the transcendence of the actual period intervals. This version of the theorem tells you that if these three n functions drop by transcendence degree m on an analytic locus of codimension smaller than m, then it must be for a geometric reason, the same geometric reasons that we had before, either isotriviality, isogeneity, or torsionness. Okay, sorry, I'm way over. Let me stop.